Okay, everyone, let's start. So, Ellie is back. So, please.
Oh, it's very nice to be back. Yeah, amazing. Okay, we've gone a long way, yeah. And by the way, if it is a little bit too much, just please ask, because I know that especially the last lecture I gave you like a lot, and now I will push even further. But I think it's good. You can take it. So let's go super quickly. I said some important things, especially. I mean, I think all of the things we said is important. But last time, like there were. First of all, okay, we learned how to make Lagrangians with extended supersymmetry, which is very nice, and we learned how to do this with n equal to 1 superspace, and we did a tiny little bit of n equal to 2, but this is enough to do what I want to do today. And then also we did these two magical things. We used the holomorphicity of the superpotential together with the symmetries, and maybe one of the important lessons that you learned is that if you make a good table, you win. So table, holomorphicity, and asymptotics. Because if you know asymptotics, you can fix a holomorphic function, yes, a complex function. So, and we did another super important thing. We said that if there is a singularity, something blows up in your face when you look at the metric of the moduli space, it's okay. It's just that some degrees of freedom became massless and you should have not integrated them out. So now it's time to take them back into account. So these two big lessons will be very important now for us. And I have to say, in principle, from here, there are two paths I could go. So there are two more lectures, so I have to choose one. One would be to do cybergology and study n equal to 1 super QCD and show you how you get the phase space and talk about all these beautiful things. This I will not do. You have to forgive me. But I will do Seiberg and Witten theory, which is super nice. And together, so today I will start with more preliminaries. So I guess it also fits very well with what Iñaki is doing. I will do baby electromagnetic duality. Like it will be nice, I think. Yes. And maybe the most important thing. So we will do. So this is the title for today and for tomorrow. And like the first thing we need to remember is we will use n equal to 2 holomorphy plus electromagnetic duality. So if you know what we did last time, to the level we did, no more than that, plus some very basic of electromagnetic duality that I will do now, you win, you can understand what they did. Yes, and maybe just say what they did is really magical. So if one of you can do something of equal caliber in the future, we win, yes? So pay attention to these lectures and get inspired. Okay, so to study electromagnetic dualities, I will start with telling a little bit about monopoles and dions. And maybe just for historical happiness, electromagnetic duality was first proposed by Montonen and Olive. And very soon there will come this word S-duality, yes? Which I guess Iñaki is already using. And this was very old. And actually, they didn't know much back then. In some sense, the only thing they knew is what Dirac said back in 33, which is almost nothing. So we have a pair. So Q will be my electric charge, and G will be my magnetic charge. I will write this down again. So they just observed this. I'm just saying some words now, yes? Just to set the... And then what this, and this is why we will learn also monopoles and dions. So the elementary gauge particles are basically exchanged with BPS. This is what this thing is. If you do this and this, they propose, oh, there is a duality there, something is happening. And I have to say, what they did was so baby, because they really didn't know much. They just knew this Manton calculation where, so you all know how to calculate if I give you two particles, classically the force between them. You did this at the beginning of your QFT class. So what Manton did is that he took two of these BPS monopole guys or dions, and you can compute also the force between them. And if you do this exchange, this force also goes to the one to the other. So they were like, oh, something is going on. Yes? And the manifestation of this, like the most clean thing, which I will also not do, is in n equal to 4 super young mills. There is a little bit about the color group going to the correct dual, but I'm not going to talk about this. If you want, you ask me later. So, and there was very important work by Sen on this, who really showed this thing really properly. Very important stuff. This was all in the 90s. And then for n equal to 2 theories, which is what we will do, is the work of Seiberg and Witten when we will do this. Are there any questions for this very preliminary introduction? This is all to be understood, yes? And maybe I will give references now. So first of all, already at the beginning of the class, I said that a lot I follow Matteo Bertolini. So he has a very nice section on this thing. And another very, very good review is the one by Adel Bilal. I have to say, there are so many reviews on the topic that what I am doing now is not nice. So yeah, anyway. And then there is the book by Tachikawa, yes? But if it's your first time, maybe Tachikawa is too much, yes? So this is not when it's your first time, yes? And I also want to give some other references, because whenever you see people from my age or older knowing something, and you don't understand how they learned it from these references. So there is a very nice review by Harvey. I give you the number. It was on a school in Trieste, and it's called Magnetic Monopoles, Duality and Supersymmetry. And there already, whatever calculations no one is showing you, they are all here, yes? So if you don't understand, you go here. And then the second thing, which is even more pedagogical, is Figueroa. So this review, it's called something Electromagnetic Duality for Children. And you need to know very basic quantum field theory to follow. They really explain everything. It's really amazing. So whenever, and like in general in your life, there will be many more things that you can find in this nice review, yes? So keep this in mind that it exists. Yes. Okay, so let's start with electromagnetic duality. And soon it will become S-duality. And we first start very basic. So we start with Maxwell equations. And I added a magnetic source just because I like it, or just because you already know the answer, what I will say. So these equations, they map to themselves if I do the following. And I guess Iñaki is already writing forms, so you don't cry you when you see. I mean, I'm not gonna really write forms. Just yeah, just for now, so that I don't have to write too many indices. Yes. So if I do this, I get back the same. And this you learn, most probably when you were playing, when you were learning E&M for the first time, you were like, oh, what is going on? Or at least this is what happened to me. I was very intrigued. So this is classical, and then we go to quantum mechanical level. And quantum mechanically, you can compute the angular momentum of the electromagnetic field, and it's quantized. And then you think that maybe you have the Dirac monopole or anything that is, some Schrödinger equation. Yes? And the Schrödinger equation, in the presence of this electromagnetic guy, it has to be consistent. It has to have a single valued wave function. And if you do this, you get the famous Dirac quantization. Okay, and there is an H bar just for now, and it will go away. Everyone has seen this, no? Who has not, who has, we ask only positive questions. Who has seen this? Amazing. If there is anyone that hasn't seen it, in the children, it's like 4 lines. It's there, it's completely explicit. Yes? And you can do precisely the same. You consider that you have a dion. And now, because I don't want to have these indices anymore, I will just use this, as I already did actually. So if you have a dion, or if you have 2 dions, in fact, you can derive a generalized 2 dions. Yes. And you can play, one way to fix these signs is to make sure that this stays nicely. So this is, I wasted a little bit of time playing around, so that's why I also wanted to write this. So now this is all very, very beautiful. But the old people would say, oh, are there magnetic monopoles? Annoying questions. But if you know your quantum field theory, and this is what we will do now, you know that magnetic monopoles naturally, of course also dions, naturally arise in non-abelian gauge theories when you have a spontaneous symmetry breaking, and this is our standard model. So this question is silly. Yes. So there are magnetic monopoles. Maybe I just write this. So this is what we will do now. We will just do this very quickly, yes? For everyone to be happy. Are there any questions before I do this? So, how do we derive that? First of all, we will start with a very familiar phenomenological Lagrangian. Yeah, they wrote this to start explaining the standard model. So, I am just writing everything. By the way, these Lagrangian look like this, and there is no bar, because these guys at the beginning, when they wrote this stuff down, they were just thinking that the color group was O3. Okay, but who cares? The same stuff that I will, whatever I will do, I will write it, goes for any color as long as you choose your favorite compact group, you win. And we will really care for these 2 lectures just for SU2. So if you keep SU2 in your mind, you are more than happy. And maybe I will squeeze here also the covariant derivative. Just to establish notation so that you can find my mistakes. This is a C. Yes, sorry for this. Is this good? Yes? So this is our model. And what we want to do is we want to do spontaneous symmetry breaking. So we will go to the vacuum where there is a VEV turned on. And I'm sure you've done this type of exercise a billion times in your life and in exams and everything. You do this, you get spontaneous symmetry breaking, and your, okay, in general, G will go down to U1s to whatever rank of the G was, yes? And in our case, you can think as U2, just one U1, nice little photon. Yes? So what is the spectrum? This is very important now. What is the spectrum? So I have this gauge field, which was in some G or whatever. And after the spontaneous symmetry breaking, what happens to it is that important, you need to split I mean, okay, this is for general. So there are the E plus and minus are the raising and lowering operators within the group. And these are the Cartans. Yes. And always these babies, they become the W bosons, the massive W bosons. And these guys, they are happy, massless photons. And maybe I just make a table because I like tables. So here is our photon. Maybe there is a tiny little bit of notation that I will always divide by this vev so that things look nice, but this is just stupid. This is just, so I take the vacuum expectation value and I dot it with this guy. So this is the photon. And first I will write that the mass of the photon is 0, and also there is no charge. Then we have the Higgs. So this is the full field, and this is just the vacuum. Yes, I project, and I get the mass of the Higgs. And again, there is no charge. And then my W bosons from here, they will have a mass, and they will have a charge. I hope this table is super clear, yes? This is what you learn in your particle physics class, and where supersymmetry wins, and we will talk about this more and more, is that this E and this lambda, they are related. Yes? Are there questions? I am going super fast because I assume you have all done this type of calculation a billion times in your life, yes? So now, the first thing that we need to write down is the stress energy tensor, and in fact, we don't care about the whole thing, we just need the 0, 0 component. And you have also done this again. Just a little thing. I here is the, mu is 0 is time, and this is the space, yes? Maybe I put this down. Doesn't matter. No, the half is here. This doesn't have a half. Yes, you have done this calculation a billion times. Now, maybe, okay, you just. So that you can keep track of the minus signs. This is how my minus signs work out. So, if you have a vev, but the electric and the magnetic field are 0, there is no energy density nowhere in your vacuum, yes? By the way, I'm assuming that the vacuum is a constant, yes? Like here, like an A, yes? So that this goes to 0. And, sorry, I was super fast. I chose this so that this is 0. Such that this is important. Without this, we go nowhere. Yes? So this is how far we can go with this type of vacuum with no electric and magnetic field, but now we will want to see if we can turn them on. So this is the Lagrangian, and now we will discover that there is another vacuum solution, the one from 't Hooft and Polyakov. Who has done this in a class? Okay, it's very good that I'm doing this. Very good, okay. There are, the reviews that I gave are enough, but they are also some very nice quantum field theory books that they have this. And by the way, this is as ancient as our supersymmetry friends, yes? This is when the first supersymmetric Lagrangian in 4 dimensions were written, yes? The Uesumino, yes? So we do this. So we start with a Lagrangian, I just deleted. We give a wave, we go through spontaneous symmetry breaking, we integrate out the heavy guys, and we end up in the IR with a bunch of photons, or 1 photon if we started with SU2. One thing that is very important is for this choice of the photon, the way I write it there, it's a tiny little calculation that I will let you do. So for the photon, which is this equation there, yes? Okay, I write it, sorry. So that there's no... So for this baby, you should write its F mu nu down. And the first bit that you get is the one you know and love from electromagnetism. Yes, as always. But there is a little bit more into this. And this is what is going to give all of the non-trivial effects. When I write this cross product, what I really mean is that there is another epsilon. There is an epsilon here that, so it makes this antisymmetric, epsilon alpha A, B, C. So this guy has a B, this guy has a C, and it contracts to this with the A. Yes, this is what I mean. So now this is the guy. And you can take it, and the first thing you can do with it is you can very explicitly check that it obeys Maxwell equations in empty space with no sources. But this is very good, because now you can continue. And you can try to look for non-trivial solutions, not just because of this ugly or beautiful, depending on how you think, part. So, so we are looking for soliton solutions. What does it mean when we have a soliton? Energy more than 0, so not this annoying thing, a little bit positive, yes. And in general, for 3D solitons, we impose 3D symmetry, yes. And of course, we are looking for a static solution to make life easy, and then if you want, you can boost as much as you like. So we want static and yes, yes. So this is the same thing what you do when you look for the Schwarzschild black hole. Maybe you've done this more recently, or when you learn instantons, you impose 4D here, and yes, the static goes because this is a 4-dimensional thing. Yes? And by the way, these solutions that I will explain now, people don't know how to do it analytically. They only solve numerically, but you can impose, I will make pictures. So this is the things that we will find. So first, I will plot the field phi in the radial r, yes? And basically, the property of it is that it will saturate this vev. So at infinity, it will look like I just have phi is equal to A. Maybe here I should and like this is the novelty, this is why we are doing this, that we want to have a solution with a magnetic charge. What did I do? No, the phi vacuum is a constant. So very naively, for example, if you are doing the O3 stuff of these guys, no. So if you are doing Georgi Glashow, this is what you get. If you are doing SU2, you can do this, and so on. Where? Where? Here? No, this should be perfect. And it's precisely also normalized so that this ugliness will go away. It's made to be true. And this is a calculation, so you just take this and you plug it in. No, this should be almost obvious. Okay, but I don't want to do this. So you take this and you dot it with a non-abelian, and you should just get this. Bam. Sorry? This derivative acts on this, and this derivative acts on this. Sorry. Okay, you are right. Okay, I didn't see this. You're right, very good. Very good, yes. Okay, so this is the correct answer, yes, thank you. Here, I mean, I'm sorry, I will put this back. I really mean this, but now this is not the constant vev that I was describing here. Now I am looking for a solution. I am looking for such a solution. Now that I will draw it now. So that's not a constant. Yes, sorry. Yes. At infinity, what you say is correct. So at infinity, sorry, here. Okay, as good as I can draw. So asymptotically, B will go to 0 nicely, but it has a profile. And that's what I want to achieve with this. Yes? So vacuum there just means that I'm doing a classical calculation. Yes? And around that, I will do my quantum field theory. That's what it means. Nothing more at this moment. So there are such solutions, is the point. I am not going to describe to you how to get them. What people do is that they impose asymptotics around r is equal to 0 and around r to infinity. R to infinity is your wish to have phi is equal to a and b going down with 1 over r squared so that there is a monopole. And then numerically, you can show that there are such solutions. Nonetheless, even though you don't know the precise form of these functions, you can say some very important things, and this I will tell you now. So, what are these things? The first thing is that I can compute of such a solution with this F mu nu there. I can compute the magnetic charge. And that I do by Gauss law. So there is nothing more to know than Gauss law. Yes? So I go at infinity, yes, and I apply Gauss law. This is my beautiful equation. Now, this B, using this definition that I wrote there with the epsilon, with the signs that I wrote there, I take this F mu nu there, and I plug in the first bit, of course, goes away. So there is this, integrated, very importantly. Yes? And what is amazing, I am not going to prove this. If you have not done this, actually what I'm doing is very bad that I'm not going to prove it, but maybe we can prove it in the social dinner or something. This integral is a topological invariant. So forget about these crappy coefficients in the front. I mean, if you have done instantons, this is identically the same calculation. That's why anyway, I'm not doing it because I don't have time to do all these calculations. It's an integer up to some pi's. And in fact, what it does is that it counts. Let's write Z. It counts precisely the map. You have this field. You go to infinity, and it counts how many times it can wrap around the S2 of the boundary. Yes? So it does precisely this calculation for you. So, and in the end, you get this. Is this okay? If you have never done this calculation, this is a calculation that is very important to do. And I mean, it's also in the electromagnetic duality for children, or I can point in every quantum field theory book that has this thing has it. It's very basic. So this is very nice because now I have here my beautiful guy. Are there any questions? No. So if you have this, now, so we have for sure something that looks like a magnetic monopole in the sense that it has a magnetic charge, which we just calculated, and it has this integer thingy. And by the way, just look at it also. If you bring the E from the other side, you have the electric charge times the magnetic charge is equal to integers. This looks very much like Dirac, up to an overall 2 that you can stand wondering what is going on, but don't do that. It's a waste of time. Yes, so this is what we see, and it's very nice, quantized, everything is beautiful. So Dirac is right. And now we take this. So this solution that we have here, that I just plotted for you and I didn't describe more, it doesn't have this, and we also choose it so that this annoying guy is 0. Yes? And of course, this in the end will be 0 far at infinity. So what we do is now we will calculate the mass of the monopole by doing this integral. Yes? In this background where there is no electric field and this chow is gone. And this is what we have to calculate. Yes, this is what we have to calculate. Now, here you do the trick. The trick that you do is you complete the squares. This is the most famous trick in our lives. So we do this, we complete the squares. I write it like this, it doesn't really matter. I write it like this. I didn't do anything, yes? I just reorganized. Oh, but now comes this guy Bogomolny, and by the way, these guys Bogomolny, Prasad, and Sommerfeld, this is what they did. It's just that we use the things for supersymmetry because it really is made to be supersymmetric. So, and this guy Bogomolny says, let's take this and set it to 0. What happens if this is the case? First of all, you have to check that this is allowed by your solution. And indeed, this is possible. If this was not allowed, we would be out of business now, yes? So if this is allowed, then I am only left with this. And so let's say here, now what I do, okay, I will delete this, it's okay. Now what I do is that this bit is gone, it's a square, so this is important, that I will set to 0. I will go slower than that. And I have to only deal with this guy. What is this guy? This guy, remember that B is the magnetic field and it obeys Bianchi identity. Yes? From there. It obeys Bianchi identity. So if I do that, I get that this is bigger or equal. Equal is when the Bogomolny equation is satisfied. Bigger when it's not, but it's a square so that it's okay. Yes? Then the integral, the half is okay. Pi. Okay, I just write the answer very quickly, like this. Where what did I do? I used that V is the vacuum, and yeah, that's it, nothing else. So I wrote it like that. And so this now, because I did this calculation for you, this is A times G. And G is here, that's why I didn't delete it. And you can also write it like this. This is the mass of the W boson. Is this okay? So just an observation, if this is okay. This equation here, especially here, we look at it, it has one of the over the electron charge in the bottom. So when we are in the weak coupling, the E is very small. This means the mass of the W is the scale in which we play, like the electroweak scale, whatever. So this is 1, let's say. So this is very big. The mass of the monopole is very large. So the monopoles are semi-classical particles. They are big particles, yes? We can do quantum field theory around them, but in the weak coupling regime, they are big. Is this good? No complaints. If there are no complaints, we can do identically the same for the dions. Just do it very quickly. No problem. By the way, when I was writing the notes, I've observed 74 is where these guys wrote. It's like in the past when Witten or Maldacena, now you don't live these days anymore, but when I was a PhD student, Witten or Maldacena would put out a paper and then we had to go very quickly to write a paper after that. So in 74, Hooft and Polyakov were the equivalent of Witten, and then Julian and Z. They went very quickly and they did the generalization, so the dions. Yes. So let's do this. So these are, again, monopole solutions which have a magnetic and an electric charge. Yes. How do we get the electric and the magnetic charge? Again, we do Gauss law. By the way, what is really important, I really didn't write to you these crazy solutions, but the point is that what I do, nobody cares. I am just using Gauss law, and I'm also using this topological property, nothing else, so then I can get my integers up to the coefficients that I carefully extract. There is no more smartness than that in this thing, yes? So again, Gauss law for G and for Q, these are the same way. So again, the same here. I am writing them together so that I can go faster. And here I do what I did before. I do Bianchi identity. And I convert more correctly like this. Like this. Yes? And again, the same calculation. So the mass of the dion. Oh, I am not going, no, I will squeeze because I'm not going to do the calculation. So the mass of the dion, again, we do this. But now we have a non-zero both this and this. So when we extract this baby, we do it twice. So what you get, okay, I'm sorry, I am just putting dots, otherwise it's too much time. We get the A in the front, okay, so the only important thing is that you massage so that you pull out a square. You complete the square. This is the point in this life, yes? You complete the square. By the way, this, you don't need it, but just for fun or curiosity, this is this. But you do not need it for anything that I will say. You just say, oh, I just want to pull out as much squared as possible. That's all you do. Yes? So let's write this nicely. So this is the BPS inequality. So this is my VEV. And of course, the sine and the cosine, we wrote it like this because we know the beautiful identity sine squared plus cosine squared is equal to 1. And this is the famous BPS bound. Is this okay? I know that this was fast, but I think, okay, I hope I said all of the important things. Is there anything important that is missing right now? Or is it super clear? Super clear.
Now are you considering exactly the satisfaction of the bound?
I mean, this is just what it is. For what I will do, when I will go supersymmetric, I will care about the bound. But right now we are talking about a phenomenon. And there are monopole solutions that do not have to satisfy the Bogom-Only equation. If they do, there is extra happiness. And that happiness is that they have this very specific form. I mean, in some sense, the only thing that you can say is that it is magical that just normal quantum field theory has a bound without supersymmetry. This is magical. Yeah, and this is somehow deep. Okay, if we are happy, I will tell you about the Witten effect. So the Witten effect. Which is when we turn on the theta parameter, the CP violating theta parameter, and we will see that something happens. And this is also another important moment in our lives when we learn this new phenomenon. So we take our Lagrangian Giorgi-Glasso nicely, no problem, and we add the famous theta term. Yes, we violate CP, great, amazing. Now, we do the same calculation as before. The fastest way to see the answer to this calculation is to remember that here there was 1/4 F mu nu F mu nu. So you can very quickly, I shift my equation, when I do equation of motion for F, by this. Yes, this will go away. So I will shift it by this. Yes, this is what happened to me, no problem. So I do the same calculation, and this shift is precisely captured in this equation. And you know, even the 4 is here. Everything is in front of you. Yes? Is this super clear? Just think that you are changing the equation of motion for F mu nu. But now this is huge. This is huge because we have this very beautiful equation. And let's, so whenever I write n is an integer, and wherever I will write m is an integer, I'm sorry. So let me write m there, yes? For that integer, and I will plug in because I have n here. So what happens? Sure, maybe I will write it slightly nicer. Yes, so this is a very beautiful equation. And I will give it a name. I will call it star because I will use it in a second. So what happened is that in the presence of a CP violating theta angle, the electric charge got shifted by something that is related to the magnetic. And even if we are not doing supersymmetry quite yet, I will just write things in a slightly more beautiful way, anticipating supersymmetry. At this stage, this will be just a rewriting of things. So just recall our friend, the holomorphic coupling. Now, instead of g squared, I just wrote e squared there because this is the coupling I have, yes? So what happens if I use this guy? Life starts becoming super beautiful. So let's first, just because I know the answer, let's form this. This is very easy. I use this beautiful guy, and I get E n plus tau m. Oh, it's already looking nice, yes? And then my bound, which is like this, now in this complex number way, it became super beautiful. Yes? And I will make a couple of more comments. We don't have supersymmetry yet, but I will make them because I cannot hold myself from that. So first, we remember we did Because you see, also people didn't know. They were just playing with these equations in the past. So there was an amazing paper by Witten and Olive. This is 78. And by the way, the title of this paper has to do with central charges. So back then they didn't know how to write the algebra. So I just wrote for you the algebra with the central charges. I wrote for you this. And for us, at this age, this was so easy. But they didn't know this, so they discovered that this has to be there by playing with the monopoles. That's how they discovered this. And in fact, they calculated, so you see the mass of the dion is equal to something. They calculated and they showed that this is the correct Z. So M is equal to Z is equal to this. This is, and this is an exact equation. And of course, when there is supersymmetry, you can really check this to death. Yes, please.
When you find the new Lagrangian, you somehow shift and then you use the G from before, right? From just the Georgia equation.
What is G?
G equals to 4 pi E n.
Yeah, but you can say, oh, I don't believe anything. I recalculate everything from the beginning. It's just that because I know that how things shift very, very quickly, I just calculate how the equation of motion for F mu nu shifts. And that's a very fast way of doing it.
Okay, but then you use the G from before the shift, right?
Yes, so I compare what I had before. So the F mu nu that I had before, I compare it with the new F mu nu that is shifted by theta E blah, 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 F tilde. That's all I did. And it goes bam. There is nothing to do. Yes. If these things are fast, have a thought and we should talk. These are super important things. They should become super clear. Even if we don't learn Cyberwitten in the, I mean, okay, we will, but this is more important. Yes, this is more important. This is basic quantum field theory. Yes? Okay, so now that we have all of this, and now that we have this amazing, beautiful equation, we can talk about the electromagnetic duality or S-duality, and we can start discovering what these guys, Monon, and Olive, started discovering, and they were very happy. So first I will make some, stupid comment without supersymmetry, and then we will add supersymmetry and we will go crazy, yes? Okay, so the first thing that we need is to talk about also the theta shifts. So if you say that theta goes to theta plus 2 pi, this is like it leaves the path integral invariant, right? Because this is the instanton baby and it just gives integers. So path integral times e to the 2 pi I integers is nothing, yes? We are all very happy about this. So that's that. Now we take my beautiful equation that I named and I plug in theta to 2 pi. What happened? Basically what happens is that n goes to n plus m. Yes? And this, I can also write like this. And maybe some of you already know this thing. Or maybe Iñaki already wrote it. Or not yet. Okay, it's coming, it's coming. Okay, so this is the T transformation, and it's clearly, it leaves the path integral as it was. And now we have the S duality, as we will learn to call it, which is basically just the electromagnetic. So we just send, we wrote it already. That's it. And at the level of like classical electrodynamics, we want to send E to the 1 over E, right? We want to make weak strong. And at the level of tau, which is the beautiful one, it sends it to 1 over tau with an overall minus sign, just because we had this little I there. Yes? So this is like this. And at the level of matrices, this goes to like this. And this is the S element. With a minus in the one of the two guys. Yes? And the important thing is that these two guys together can generate for you a big group. Yes, and this group is parametrized. I mean, it means that they are 2 by 2 complex matrices with the determinant being 1. Yes, and at the level of tau, this is like this. So now we went crazy. We found that, oh, it looks like, at least at this super stupid semi-classical level that we were doing there is the electromagnetic duality. We added a theta term. This is the symmetry of the path integral. So in a very stupid, at this stage, completely semi-classical level, it seems like there may be happiness. Yes? Completely semi-classical, completely stupid at this stage. But it is. And that's why this Montonen and Olive, they said, oh, there is this... Yes? And I told you also they had this Manton calculation where the Manton computed the force between two monopoles. And the force between two monopoles, under this, it maps to the force between two normal particles. So they were wow. And by the way, when I say this, all of the big discoveries somehow in the past, or half or something, they have been done by computing the force between things. So, for example, Polchinski, his famous paper, what did he do? He took two D3 branes or whatever DP branes, he computed the force between them. He did the same thing for two supergravity objects, and he said, oh, DP branes are the supergravity solitons. Yes, so anyway, This is a comment, a historical comment. So here it was the same. Sorry? Yeah, so when you don't know what to do, compute the force between the two particles, and maybe you will make the new discovery. Yes? Okay, so up to now, no supersymmetry. Let's add it. So we will add it, and we will see how far we can go, and we will, amaze ourselves. So what is very important to say is that this Lagrangian I just deleted. So this Lagrangian, let's write like this, theta term, so that I don't write the pi's again, is basically, you can recognize it as the bosonic part of the n equal to 2. I will write it again in a second, I will remind you. So if we have a consistent way to switch off the fermions, to set them to 0, we have embedded all this madness that we just did into supersymmetry, and this is amazing, yes? And this is the minimal setting for it. Of course, you can grow bigger and you can embed it in n equal to 4 or other things, but this is definitely there. Yes? And just one tiny little difference, but in some sense there is no difference at all. Now, the V now is not how I was writing before. It comes from our favorite, we were writing the scalar potential, and we were writing it like this, with a correct 1/2 factor that you asked. Yes, so we had this. And for pure, there is no superpotential, and we had only a D term. We have come really far, if you think about it. Yes? So there is only a D term. And then if you demand that the D is equal to 0, you find that this is a beautiful solution. And these were the supersymmetric vacua. Yes? And I don't remember, honestly, if I said the word Coulomb branch or not, but this is what is called the Coulomb branch. But it doesn't matter at this stage, who cares? It's a name. This is this. And what is very important we said about the supersymmetric vacua is that these are nice vacua that, first of all, they define a moduli space, and they preserve supersymmetry. Great. How am I doing with time? It's not okay, it's okay. So, as we have done everything, we can have now, you just, with your imagination, we don't need to write anything. We take the Lagrangian of n equal to 2 pure Young-Mills. It has nice monopole and dione solutions. And maybe one comment that it's definitely worth making, and maybe I will make it many times, is this Bogomolny equation. You can obtain it, because what did I say? I made a comment, if we could somehow get rid of the fermions. This is what I said, yes? Yes? So how do you get rid of the fermions consistently with supersymmetry? Of course, you can say, oh, I put all the vevs to 0. Nobody would say anything to that. But that's not enough. Supersymmetry gives something here. Yes? And this something that it gives is precisely the Bogomolny equation. Yes. B or, okay, I write it. I. Up to factors now, yes? You have to forgive me. Anyway, something like this. I want to be nicer than this or not? Okay, I don't want to be nicer than this now. I can fix it, but I don't want to waste time now. Is this okay? So this is precisely what you do. So by the way, this part, we did it because I explicitly wrote down for you the supersymmetry transformations of the chiral, but I didn't write this part for you explicitly, but this is the F mu nu that I have written 10 billion times, yes? So this is how it works. What is the time? Okay, super quiz, just to make sure that we are all happy. So, what is the field content of n equal to 2 pure young males? Just shoot answers to me. Quiz. Perfect. And in n equal to 1 superspace, how can I do this? I can have a chiral superfield and a W alpha. And we did something amazing. We put them together in an n equal to 2. We defined, if you remember, this special Y guy. So they are both chiral. Yes? And we beautifully put them together in this plus some annoying auxiliary field, but whatever. Yes? So this we know. There is another very important thing. Okay, I can go in components with this thing. Maybe I don't do this now, or maybe I do it so that I can write things nicely. Sorry, now I am thinking what I can do fast, but I think it's not a nice way of proceeding. So these are my fermions, and this, one of the things that I want you to remember is that this is an SU2 R symmetry doublet, yes? And then I can continue and I can write 2 theta terms. And here is where I have packed all of my auxiliary fields. This is a triplet of SU2, and it has F, D, and F bar in it as a triplet, yes? And the same way, but now I don't contract this, but I contract this. I have this guy here. The F mu nu, the self-dual part, which are projected with S mu nu, sigma mu nu on it, yes? Plus dot dot dot. I don't care right now, but this is what we have, yes? And we know the SU2 R symmetry. And why I am writing this? Because there is one thing I didn't tell, because I went completely fast last time. I didn't talk about the U1 R symmetry. And this is important now. Because if you remember, I said that whenever we have an algebra with n extended, un is the maximum, and for the n equal to 2 case, you get the full u2. So this is the SU2, and this is the extra u1. And the assignment is like this. You can actually, the assignment, you can sort of almost freely choose, but this is a choice. And this choice contains also a choice for what is the u1 for theta, the way I wrote it, so that you can go down from 2 to 1 and so on, yes? And yeah, okay, maybe that's enough. And I will start writing a little bit the Lagrangian, because I need it a little bit. And by looking at the Lagrangian also while I am writing it, you can check that I am writing or I am telling you the truth in this blackboard, that there is indeed this U1. Yes? So while I write, you check me. So what did we say? We said that, and let's write a trace. This is what we said. And we said, oh, look at this. This is holomorphic. This is very, very nice. This is what I'm going to use. And we also said that you can write this in an n equal to 1 language. Not fitting. No, I will write it under. Yes? I will even be more brave, and I will write all the components so that you can test me like crazy. And I am writing super fast here, so if I write something bad, tell me. And there should be somewhere some parenthesis closing. Yes? And we should be fine with all of this. Are we fine with all of this? And explicitly, let's check, look at these beautiful babies here. Let's look here. This is a sneaky guy. First of all, it has explicit SU2R symmetry because of this epsilon, nothing to do. But also, if phi is 2, -1, -1, 0, U1 are symmetry. Okay, this is more trivial, and this is more trivial, yes? So we see with our eyes that we have an extra U1 explicitly. And always, when you check these things with your eyes quickly, you go to Yukawa. Okay, I want you to finish writing so that you can pay attention. So one thing that already I said this comment is that when we were doing the Georgi glass show, we had an E that was, in the D in the covariant derivative, and we had a lambda that this was inside the V. Here, Okay, here everything has 1 over g in the front, but if I would rescale the fields the way we said, the E and the lambda would explicitly be equal to each other. Yes, so there is only one coupling constant. This is because of supersymmetry. And this beautiful baby, when there is n equal to 2, it can be written in the very first line. Yes, and it's holomorphic. So what did we do? When things are holomorphic, we win because we play the holomorphicity game. So what did we do when we, for example, proved our non-renormalization theorem? We said the superpotential is holomorphic. It can be function of all the stuff, but it has to be holomorphic. And I simply impose the symmetry of the model and asymptotics. So I'm going to do now the same, but in an n equal to 2 way. What is the same in n equal to 2 way? We start in the UV with this model as written up there. So this model as written up there so it's a holomorphic phi function of psi at the UV. This I maybe already said, this is called prepotential. But it doesn't matter, this is just an annoying name. Who cares if I said it before? But this is what we have in the UV. And then what do? We give a vev yes? We give a vev, we let go the RG flow, all the massive guys get integrated out, we go to the IR, and what is left? A beautiful massless, now n equal to 2 photon. There is a very important paper of Skenderis and friends that has the title How to Go with an RG Flow. So how to go with this RG flow now? We get the Lagrangian of an n equal to 2 photon in the IR. This is an effective field theory. Yes? But it's n equal to 2 and it's just a photon. So this will be holomorphic. So whatever stuff in this life, precisely like we talked about the superpotential, its couplings, its lambda, the scale, it's the psi, the superfield, they will all go here in a holomorphic way. Yes? Is this okay? Now, if this is the truth of life, I will do, okay, this is too, maybe I will do a little bit. I will go down a little bit with you in the level of complexity. Are you happy with this up to now? Is there anyone that wants to say no? No. So let's go a little bit. So this is our friend, and this can also be written okay, I wrote here IR, but let's drop this. It's the IR, yes? Let's stop writing things when we don't need them. Do you all agree with this statement? It's as stupid as what is written on the blackboard, but super important. Like all of the physics is already there. Are you okay with this statement? Let me write another statement that I want you to be okay with in now components, because we can do everything in this life. Real. So by the way, when I write this junk, I mean the whatever is the effective stuff that stands in front of this, yes? I will talk about this more. It's coming. And okay, I stop writing. I could write the same thing for the fermions. They all have the same. You allow me. If I have this you agree with the following definition. Yes? So you from here, just because of this. Complaints? I delete this then, because I was going in parallel. So these blackboards are free now. And by the way, F, it doesn't matter if I write it as a function of the superfield or of the crappy vev, it's a holomorphic function, yes? So when I write also this, so df dA bar is equal to 0. This is what I mean, yes? Holomorphic. And it comes from the big level, from the superfield level. And also, there is something else that is very important. If this is true, because tau A, you have to take derivatives. So this is derivatives, yes? This, what I mean by this is d squared dA of f, yes? This is what I mean by this. Sorry, this is maybe a little bit fast. But now, if f is holomorphic, this means is harmonic. And at this stage, this is an annoying statement that Elli is making, but we will use it. Yes? So write it down. Yes? And another little statement that again I will make, but we will use it. So this, what we are doing here, is we are deriving, this is a sigma model for the IR, okay, it's a baby sigma model because there is only one n equal to 2 photon, but for that guy is a sigma model, and it has a metric, a target space metric. And the metric is scalar from n equal to 1 supersymmetry. We did this. When we did n equal to 1 chiral superfield, no way out of that, right? And we really proved that if you have this k Kähler potential and you shift by holomorphic plus anti-holomorphic, nothing happens. So this is the symmetry of the model. So the metric of this target space is really, parameterizing a Kähler geometry. Yes, we did all of that. And in this case, this Kähler geometry, okay, it's a one-dimensional object, is this. And I can also write, it's the same, I'm exaggerating. Yes? And one absolutely last statement. If this is a metric, and I define a Hilbert space out of it, what it better be? It better be positive definite. I will write here, metric good, like UG, positive definite. So G phi phi. And this I will also use, it's coming. So now, this, in some sense, this was the review, but intense review, with also sort of bringing it to where I want. Yes? And maybe I want to do one tiny little last bit about review. We didn't only learn the massless n equal to 2 vector multiplet, we also found that there is a short massive n equal to 2 multiplet, and that has precisely the same degrees of freedom. I wrote the sentence, I will write it again. As the n equal to 1 massless is just a slight reorganization. And I also said that because of this, there is no Higgsing from someone outside. This multiplet is doing self-Higgsing. So you give a vev to the scalar, and that's how you make it massive. Do you remember all of this? So I will write it one more time so that nobody will ever forget this. And then I'm done with review, and then we solve the model. Or we start solving today. So one last recall. And why do I say this statement? Because I wrote at the beginning that these guys, Montonen and Olive, they observed that if you exchange the elementary particles, the elementary photons, with the BPS massive guys, this exchange completes the SL2Z duality, yes? So that's why we need this. To vector. So here is the 3 plus 2 while. This is precisely equal with the n equal to 2 it can Higgs itself. So you start with a complex baby here, you Higgs, you get what you wanted. And this is a very, for me, this is very beautiful because nothing of what we did last week is useless. We use everything. Yes, so this is extremely nice. And okay, I will say one thing for the people who can keep it. For the people who cannot keep it, it's okay. This is an advanced statement. So because what we are doing now is perturbation theory, and we are looking at multiplets. In perturbation theory, you can never, if you have a multiplet, you can never create new degrees of freedom. It's constrained by representation theory, which is bigger than you. Yes? So if you begin with an n equal to 2 massless vector multiplet, and you do normal things, what we do in QFT, you can never destroy this degree of freedom counting. Never. Yes? There is one thing to be very careful about when you have moduli spaces, either of vevs, which is what we do now, or of couplings, which is, for example, a conformal manifold. There are special points, but as long as you keep away from special points, these multiplets will never go away. They will be there as they are. So what we do is really rigid. There is no way out of it. So where are we? We started from the UV Lagrangian that I'm deleting now. We said that we give a VEV, we go to the Coulomb branch, we let it flow, we are in the IR, and we want to figure out the effective theory of this IR photon, and we want to use holomorphicity. Yes? And what did we say? We can fix a function in complex analysis, as long as we know that it's holomorphic or meromorphic or whatever in the domain. But we also need the asymptotics. So in the example that we did with the Wezumino, we checked weak coupling and we checked masslessness. Let's forget about the mass for now, because it's all in the vevs. We need to check weak coupling. So let's do this. This is very important. Oh, I'm going too fast. No, no fear, I go fast. Is this okay? I go fast. And actually now, as opposed to what we did with the Wezumino, we will do something slightly more advanced, and we will not only keep the tree level, we will also keep the one loop effect. And this is important because this is what separates actually n equal to 4 super young mills from n equal to 2. But you don't need to know this, we will just do this. And this one loop computation is the Coleman-Weinberg computation that we learned. So all we know in life is we know that there is this massless photon. And what did we say we do? We draw all the diagrams, which happen to be polygons because of the happiness of superspace. Massive guys run in the loop. Massless, which is our beautiful photons, go outside. It's really the same thing that I did in the example. All polygons. We do this. And it's precisely the answer also. Okay, let's write proportional because I'm dropping all the factors. This is what you get. And I will give you here a little reference because it's a beautiful paper where they do these calculations. And they do it both in n equal to 1 superspace and in n equal to 2 superspace, so you can be super inspired by them. And maybe I just write also here so that it looks nice. The full answer, full glory, is this. Again, this is one loop. And what is new with what we did with the Wes-Rumino last time is that the scale also explicitly appears now. This we didn't have before. It's the first time we see a scale. Of course, we skipped many things. This is why we didn't make examples with scales. But in the context of Coleman and Weinberg, this is supernatural because this is the same like what we did last time for this other model with phi 1 and phi 2 and waves and everything. Are there questions? So we have nothing to do other than start with this weak coupling and impose electromagnetic duality in a super smart way. This is like why Seiberg and Witten are genius. And we will completely solve this problem. And you know, the level of what we are doing is really the same level with the level that we found that the superpotential is not renormalized. It's the same, yeah. It's just that in some sense the complex analysis is a little bit harder. But I am with you here, no fear. Yes? So I will write some words so that we go smoothly. So what they did is basically they precisely computed, if you wish, f of a, or better because we don't really care about this. Like not only, like full glory, not only in the weak coupling, but exactly. So this is the weak coupling, yes? Like including non-perturbative. In this case, instantons. So what I am telling you is if you start with this and you impose electromagnetic duality, and of course holomorphicity goes without saying, you will discover all the instantons. This is what I'm telling you, which is insane. I haven't said anything about instantons, but we don't need to know them because they will come out. The only thing that we need to remember is that when G, the metric, or tau A, have singularities. It means that somebody became massless. And who is going to be this somebody now? The monopoles and the dions. This is what we are going to do. This is the name of the game. And this is where electromagnetic duality will do the job. And we will see very quickly. I just say the words so that you can follow nicely. When we depart from the weak coupling, we will see that tau of A, the description of it, A as a coordinate, is not good enough. We will see why. So what we will do is that we will ask for other sets of coordinates. So you can think of your moduli space. Here you can say, oh, it's nicely covered with one set of coordinates. But here, no. And what we do, and this is what electromagnetic duality will do for us, there will be another set of coordinates, the dual coordinates, where there, the weak coupling is for the monopoles or for the dions. And here we will use these coordinates. Is the logic clear? So this is what is going to happen. Okay, we are doing amazing. I will just write down a magical equation, which you can say it comes from the smartness of Seiberg and Witten. And we will use this to do the job. Yes? This equation, you can say, if you are, anyway, bold or smart like them, that it's an obvious equation. If you are not, you will say that it's magical. But it doesn't matter what you say. It is what it is. So we basically, we need this. We need to learn how to do this. Here is the answer. Is this. So up to now is what they say, this is what life is all about. I mean, okay, this we wrote it down. So basically they say, take this. If you take this, you can write down this equation, yes? And from what we did somewhere, it's gone, but tau is the two derivatives of f. And now we can do a quick check, if you wish. Oh, this is good. If I have these dual coordinates, I did what this S-duality is supposed to do. This is very good. So this is not crazy what they propose. Yes? And not only it's not crazy. No, I stop because otherwise I stop. Yes, but like sleep with this equation. Yes? Yes?